Hello, everyone. Welcome to a new session of our Gamma seminar. It is a pleasure for me to introduce our speaker today, Vera Vertesi from the University of Vienna, who will introduce us to open books. So Vera, whenever you want.
Okay, so I don't really know how much you know about open books. I was trying to start from the very beginning, and yeah, just tell me if you need more details or less details. All right. So okay, so let's just start with the introduction, and that one is starting with a little bit of history. So the first time the word open book was used was in the paper of Winkelnkemper in 1973. But the okay, 1 second, I close the door. But the exact same notion in different contexts have already been used by other papers. So this basically the same thing is global Poincare-Birkhoff section, or a relative mapping torus, or a Lefschetz or a Milnor fibration. That's in the setting of like a slightly more restricted setting of complex manifolds, or fibered rings, and the spinnable structures. They are all were words for open books, and now I think open books has really stuck to it. So that's the word we are using nowadays. But before the words existed, Alexander already proved that every three manifold admits an open book decomposition. And then in a very important paper of Thurston and Winkelnkemper, they showed that open book decompositions are a useful way to give contact structures. And their first proof was to show that every three manifold admits a contact structure. Later, and that's somehow from where we count the modernism of contact topology, is when Giroux claimed in his ISM paper that open book decompositions up to positive stabilizations are the same things as contact structures up to contactomorphisms. I'm going to talk a bit more about that. What is positive stabilization? What is a contact structure? Even that I'm gonna share. So I want to mention this because it's quite recent progress that so his original proof, which he gave, contained a couple of statements which didn't have complete proofs, and it has been hard to find a proof for it. So recently, Breen, Honda, and Huang gave a complete proof of it, not only for the case of three manifolds, and me with Licata in the same time give a more restrictive proof for three manifolds. First in a special case, and then in all the cases. Yeah, anytime you have questions, I'm very happy to answer. So do you have any questions? So if not, then let me just go a bit further and talk about what is this connection? Is basically I'm gonna sort of try to give as much details of this connection as I can in 1 hour. So the connection basically says that you have a three manifold with the contact structure. I will soon define it, and contactomorphism is the type of map which preserves the contact structure. So this is the the right type of map, like diffeomorphism for smooth manifolds is what contactomorphism is for contact manifolds. And then, as I said, and then here's a set of open books, which can be really given like with something like this, like a very nice simple picture. So Thurston and Winkelnkemper gave this connection, and Giroux gave a connection this way, and showed that whenever two open books are giving you the same contact structure, then they are related to each other by positive stabilization. the way you should think of contact structure, the contact structure is something geometrical. It's we will soon see. It's some sort of like, you know, restrictions of how the it's a plane field in the tangent space of a manifold. On the other hand, open books, they are topological, so you can forget how the three manifold looks like. You only have to locally, that's a sort of global property, and it is very often used combinatorially. I'm a Hungarian mathematician. I come from Hungary, so for me, I have a very strong combinatorics background, and most of the problems I end up doing is like translates back to combinatorics, and that's why I like open books, because it's really like a very good tool set to translate problems in contact topology into something which I can just phrase it, curves and surfaces and who intersects what and how. So it's like very easy to draw pictures and think about things. I'm not going to talk too much about these things, but but that's somehow the main point of contact structures, is like how like there are properties of contact structures, so-called, for example, tightness, which can be explicitly phrased with open book decompositions. And then there's another property of contact structures, Steinfillability, which is also completely phraseable by open book decomposition. The right-hand side, we will be able to understand by the end of the talk. The left-hand side, I wasn't planning to talk about. Okay. If there's no questions, then
maybe a fast
yeah,
question.
there is. Okay.
What sort of contact structures are we studying here? So like co-orientable or just general plane fields?
Co-orientable, and I'm going to talk about them. Yes.
Okay, great.
Yeah, we're just going to talk about co-oriented contact structures. Okay. So once you have open book decomposition, there is a lot of theorems you can prove using this nice connection between open books and contact structures. So Giroux gave this is more like a list than a Giroux gave a description of Steinfillable contact three manifolds. It's a very combinatorial description. I already told you in the previous page, so that's this that it's a positive composition of positive Dehn twists, and then Eliashberg and Etner showed that weak symplectic fillings of contact three manifolds can be enlarged to be contained in a closed symplectic manifold, and then and Event showed, these are all recent results, fairly recent results in the 2000s. He showed that contact surgery preserves tightness. Tightness is a very important notion of contact structures. And then there is a recent work which I'm doing with my student Eric Sten and Mark Kegel and Daniel Zudas. Those are professors who they showed that we showed that that you can classify Legendre surgery diagrams which are describing the same contact three manifold. So do you guys know what surgery is?
Not me, at least.
No. Okay. Yeah. So just what type of structures we're looking at. So surgery is the following operation on a three manifold. You take a knot in a three manifold. So the purple thing is the knot. Okay. So here it's this like this trefoil knot, and then you remove its neighborhood from the three manifold. So what's left is the blue part. Okay, and then you take another torus. This is a solid torus. That's the green curve is telling you that it's completely filled up here. Okay, and you want to glue this solid. So you remove the solid torus. That's the neighborhood of the knot. But now you want to glue back a solid torus, but slightly differently. So if I glued it back so that this bounce here, then I would get back the original stream manifold and I didn't do any change. But if I glue it back in a different way, so that the curve which bounds here is actually going into some complicated curve on the right-hand side, then this one gives me a different stream manifold. In fact, so every single stream manifold can be obtained this way from the sphere just by doing surgery along a link. So maybe not one knot, but multiple knots. Okay, and then also open book decomposition have been used for the following statements of showing Kronheimer and Mofka show that every non-trivial knot has property P. This just means that if you do surgery along that knot, then the Poincare conjecture is satisfied in the space you obtain. Satisfies means that that it's not S3 if yeah. So okay, so and then Ozsák and Szabó showed that the unknot, the trifoil knot, and the figure 8 knot are characterized by their surgery. So meaning that if you know what you get as the surgery, then you know what knot you started with. Okay, the Thurston norm, which is some sort of like genus of the knot, is determined by Hegerfeld homology, which is a three-manifold invariant, and then Giroux and Godman give a completely inductive construction of all fiber knots in S3, also using just open book decompositions. So this was just to convince you that there is a lot of like deep mathematics you can do with it, and now I'm trying to build up this more combinatorial structure by first talking a bit more about contact structures, and then tell you what open books are, give a lot of examples of open books, and then oh, I left out one thing. So yeah, tell you how you can construct contact structures for open books and how you can stabilize. So positive stabilization is how I'm ending. Open books. Okay, so let's start with contact structures. So here is the first picture. So a contact structure, but maybe you know more about this than I thought. So a contact structure on a closed oriented smooth three-manifold is a totally non-integrable two-plane distribution. So this just means that totally non-integrable means that it is not tangent to any surface, open surface, and the two-plane distribution would be just meaning that at the tangent planes you choose a two-dimensional subspace. Being non-tangent to any surface, okay, so being a two-plane distribution means that locally you can give the contact structures a kernel of a one form, and then non-integrability can be phrased locally as alpha of h d alpha being a positive multiple of a volume form. I secretly oriented my contact structure, my three-manifold, and in the following, I will always assume that my alpha, of which the contact structure is the kernel of, is given globally instead of just locally, and that's what makes it co-oriented. I had a question about this earlier. Okay, so locally, any contact structure is the same, and it looks like this picture here. So this is the kernel of dz minus y dx. So you can notice that so this one only depends on the y coordinate, and as you go along in the y coordinate direction, the contact structures like somehow rotate in a very specific way. The specificity comes from the fact that it has to be a positive multiple of a volume form. Okay, so otherwise, if it was a negative multiple, it would rotate the opposite direction. And this rotation is what makes what makes the contact structure not not tangent to anything. So this rotation somehow ensures that whenever there would be a surface it would be tangent to, it just rotates out of it. I mean, of course, you can phrase this significantly better by computing it, but it's a good first way of thinking about contact structures. So Darboux theorem, phrased in another way, just says that contact structures near a point, they look the same. And there are multiple other neighborhood theorems of contact structures. Not only they look the same near points, but they also look the same near so-called Legendrian knots. Let me just say what a Legendrian knot. So a Legendrian knot is a knot so that the tangent of the knot lies inside the contact structures at every point of the knot. Okay? So this would be a Legendrian knot. Legendrian. And as it turns out, so contact neighborhood theorem says that if you have two Legendrian knots and you have two maps which maps the contact structure from one to the other, then there is a contactomorphism between the two structures, which is bringing the neighborhoods to each other. So if the contact structure is the same on the knot, then they are also the same in the neighborhood of the knot. So this rotation is somehow really telling you a lot of things. It's a very, in this sense, it's sort of rigid. So the same theorem holds for transverse knots. So if you have a transverse knot, that's the type of knot where the tangent of the knot is transverse to the contact structure. So this is a transverse knot here. Okay, so here you can see that the contact structure is tangent to it, and what you get from the contact neighborhood theorem for any types of knots is that near a transverse knot, the contact structure is always contactomorphic explicitly to this contact structure. Okay, the one which is drawn here. So it's a contact structure which is horizontal in the middle. It's symmetrically rotating a number of times, and it's not going to be. You cannot make sure that it's rotating as many times as you want, but you can make sure that it rotates at least once or a couple of times. So that this radius you don't have control over. That's told by the contact structure around you. Okay. So this is called a symmetric contact structure, and this is called the standard contact structure. Was the first example I gave you, the dz minus y dx. Yeah, and then so I'm talking about contactomorphism all the time, so why don't I just define you what it is? So contactomorphism is just a diffeomorphism which carries one contact structure to the other, and then we distinguish if we happen to have the two manifolds we are talking about is the same, m equals m prime, then you can distinguish two types of relations between plane fields. One is that they could be homotopic to each other as plane fields. So you don't as plane fields, but always keeping them as a contact structure. So there's a homotopy of contact structure, and then there is the stronger notion of isotopy when there's a one parameter family which brings one of them to the other. And gray stability is telling us that these two notions are the same for contact structures. So every homotopy is induced by an isotopy of the ambient space. This gray stability is lying in the background of basically every theorem which I'm talking about, but it's very good to hide. It's hiding very nicely. Before I start my next section of open books, any questions? Okay, so if there isn't, then I'm just going to try to tell you what an open book decomposition is. So an embedded open book decomposition is a pair B and P, where B is an embedded one manifold inside. So everything happens in a so M is still M is a contact is a 3 manifold at the moment. Okay, 3 manifold, it's closed and oriented. Okay, so you have an embedded one manifold, and away from this embedded one manifold, you have a fibration. And there's a special property of this fibration that near the binding, which is this embedded one manifold, the fibration looks like this. So it gives you Seifert surfaces. In principle, it doesn't have to give you Seifert surfaces. Before I asked it could wrap around like multiple times if I wanted to. Okay, so this is what an open book decomposition is this pair. The fibers are called the pages, or sometimes the closure of the fibers, which is called the pages of the open book. Let me give you a concrete example using complex. And this is the following. So
I'm sorry.
Yeah.
The last point of the definition of open book decomposition is
Yes.
basically is stating that there exists some locally, color neighborhood of.
Exactly.
Okay, thank you.
Yes. And then there's a secret orientation in the statement too, because Seifert surface has B as a bond on a connect oriented boundary. So yeah, if B is oriented this way, and the pages are all oriented, so that it's the oriented boundary of them. Okay. So you have S3, and I'm thinking of S3 as the unit sphere in C2. So let's just take the binding, which is the subset where Z is 0, or the absolute value of Z is 0. This would be an S1. And I'm taking the following vibration. I'm just mapping ZW to Z to the angle of Z. Okay. So if you want to draw it in R3, then you have to use some sort of map of this C2 into R3, and this is the map I'm going to use. This is not very important. So what I'm trying to draw is that this is the binding, and it's parameterized by the real part of W, or the real part of W, and then here the pages are going to be this type of really like half planes given by just parent, like each page is the preimage of a concrete angle. Okay, angle being T here. Okay, so remember that we are still working not in R3, but we are working in a 3 sphere. So meaning that these pages, even though they look like half planes, they are actually just disks. Okay, so for every point you have a disk. Okay, so that might have been too easy. So let's just do something harder. So instead of taking instead of taking just z equals 0 and I'm also taking z equals 0 and w equals 0. And then I can divide by the product of them without getting anything undefined. And I'm going to take S3 minus this binding and map every point to the angle of z times w. Okay, so if you draw this, so you can this is still the z equals 0 part, and this would be the w equals 0 part. Sorry, this is the w equals 0 part, and this is the z equals 0 part. And then you want to draw the pages. So it's super hard to draw these pages. Here is one. So I want you to understand this picture. So it looks like that it's this is a sort of a disk with this part left out from it, and then there is a twisted band which connects it into this half disk here, and then there's another twisted band which connects it back. So you can see that it's an annulus, but you can also parameterize it as an annulus. I did the parameterization, so you can take, so this direction is the r direction, this is the theta direction, and you just map it here. Okay, you can check that you know what you need, that the angle z times w is a constant, and it's going to be this constant t. Okay. So, oh, and yeah, this one is there so that the sum it still lies on S3. Okay, and you can do the exact same method and get a lot of open books of S3. These open books are called or Milnor open books. So you just always take a polynomial. Oops. A polynomial with an isolated singularity at 0, and then the same method can be used. So the zeros, so the preimage of 0 is going to be the binding, and then you're just going to take the angle of the value of the polynomial. Okay, so if you don't like complex numbers, I brought you another example. But for that, you have to understand S3 in a very special way. So I don't know if you have seen this picture of S3. So I'm thinking of S3 as the following picture. So here, so this is a T2 cross interval here. So that's the T2 part. Okay, this part is identified with this side, and this top part is identified with the bottom part, and then there's an interval verse of T2s here. Okay, but then I also identify everything on the boundary here. Okay, so every red curve here on the boundary is going to be collapsed to one single point. It's drawn here how it is collapsed, okay? And every curve on the right-hand side is also collapsed on one single point. So, and every square here is secretly a torus. And okay, just spend some time and figure out why is this actually giving you S3. But once you believe me, then there is a very nice way of seeing an open book here, and that's the following. You just take the slope one curves here. So this is one of them. So first of all, notice that this one is an annulus because this edge here is identified with the bottom edge there because it's a torus there. But also notice that even though these guys seem to be lying on different levels, but all of them are identified. So it actually just has this one single boundary here after the collapse. Okay, and then the same happens here. When you collapse everything, you just project onto this part. So this is going to be some twisted square here, and this twisted square alone is giving you an annulus because still this is identified with this, which means that this part is identified with that part. So this is a very good way of visualizing what kind of twisting we have here. I just drew you another page of the exact same open book. So it's shifted and now a bit. So this is the edge. So now this part is identified with here on the top. And again, it's a twisted, it looks even more twisted here. The picture looks like, okay. I hope one of these examples made sense for you. Any questions? So if this is too abstract, then we can go even more abstract, but somehow a little bit easier in some sense. So let me just explain how you can think of open books from a viewpoint when you don't see the manifold yet.
Yeah, sorry, one
Yep.
quick question. I mean, the first two examples were examples of trivial open book decompositions.
Well, this one was trivial open book decomposition.
And
Here, but this one was an annulus already. Or what do you mean by trivial?
that the vibration is trivial. I mean,
Why trivial? No, I mean this one is. Oh, so these two pictures. So this one and the one here, they are the same open book, just described differently. So this one also has a lot of twisting in it when you look at it, how it wraps around. Oh, actually I have a video here. Yeah, very good. Okay, so here, so this is how it sort of looks like near the, do you see this? So it has a lot of twisting near the pages. Yeah, I wanted to show you this too. I forgot it. So, for example, here, this is an open book for the 3 torus. So the 3 torus is like, you see the cube here, and then it's top and bottom and back and forth is all identified with each other. And then you see how the open book is absolutely not trivial. You see how it's like twisting everywhere. Okay? Maybe this helps. Yeah, that was it. Does this answer your question?
I mean, yes, thank you.
Yeah, okay. So an abstract open book is just going to be, so you fix a, yeah, so you can, whenever you have an embedded open book, you can construct an abstract open book from it in the following way. So you declare one of the pages to be your page. So, like the time0 page, for example, is going to be my chosen page. And then I'm going to look at the first return map of as I turn around. Okay, as I go around. I mean, I have a vibration, and I'm going to look at the first return map of this vibration. The first return map for the vibration gives you a map from S, which is this the chosen page, to itself. That's the map phi, and this map is going to be a homeomorphism that fixes the boundary. Actually, I can make sure that it, because of the local model near the boundary. You remember near the boundary, the open book always had to look like that. So I can make sure that not only the pages fix not only the S is fixing the boundary, but it also fixes the neighborhood of the boundary. And then, forgetting the whole story I told you before, I can just define an abstract open book to be a pair of page, which is then a surface with boundary, and a monodromy, which is a homeomorphism that fixes the neighborhood of the page. So, in this case, the previous example is giving me, so the page is going to be an annulus. And what is the first return map? Well, that is significantly harder to tell. I'm trying to convince you that the first return map maps this curve this curve A into here, this other curve phi of A. Okay. So the way you do it is that, so here's my curve A here on the page. Okay. And now I'm trying to follow what happens with it when you do the entire vibration. So how do you follow? Well, what you follow is that the endpoint cannot change as you move forward. So you're going to have these like different sections. The endpoint cannot change, so it has to stay here, and the endpoint cannot change on the other side as well, so it has to stay there. And at the end, it's gonna be like, you know, A cross interval. Because so I have to draw a square with this type of endpoint. So I'm just looking at how this looks like. So here am I. This is how it ends on the torus edge. It's gonna come back here. And this is how it ends on the other edge, on the bottom of the torus, and it's gonna come back there. And then I'm just continuing it, and it's gonna look like this. Okay, so there is here. So what I drew is a disk, or rather than a disk, it's a rectangle embedded with the given boundary conditions, and I have no choice of how I'm doing it. This is like just forced by how the vibration goes. So this is the return map, and then you just read it off that this is A, and this is the image of A, which is exactly like going once around. Okay, it's very important that it goes around in the right-hand side, towards the right-hand side. So this map is called Dehn twist, as we will soon see later. Yeah, a right-handed Dehn twist. Okay, so let's talk a bit more about abstract open books. So if someone just gives you an abstract open book, so remember that was a surface together with the monodromy map, which was a homomorphism which goes back to the surface and fixes the neighborhood of the boundary, you can define a three manifold. And here's the way you define the three manifold. First, you form a mapping torus. So this is my surface, and it takes the surface cross interval. This is the surface cross interval, and then I glue the right-hand side of the picture to the backhand side, to the left-hand side of the picture with the monodromy phi. Okay, so point X is going to be mapped to phi of X, and then those 2 points are glued together. Okay, that's what's written here. So you remember, phi fixes the boundary. So meaning that if I take a point here, then it's mapped into the exact same point there. Okay, so these lines are gluing into circles. Okay, so this is going to be some sort of circle. At the end, so I'm going to have, this is the boundary of my mapping torus. And now I'm trying to collapse this boundary of the mapping torus. And it is going against any of your intuition how you would collapse it, because the nice way to collapse it is just to close up this circle, but that's not what we're doing. We are exactly closing up the other circle. So we're going to close up this circle here. Remember, this is a circle because everything is fixed. And I'm going to make this into just 1 point. Okay, so I'm collapsing this to 1 point, and here I try to draw a picture. I don't know if it's helpful or not. Okay, so you can see that the common binding is not just one thing. Okay, so what you're going to get is, now you are getting a three manifold. I mean, it's a three manifold because this one was a three manifold with boundary, and now I just got rid of the boundary. But it's not only a three manifold, it's a three manifold with an open book decomposition, because the open book decomposition is just right on the nose. So yeah, so the pages are going to be exactly whatever is left from this. These are going to be the pages, and then the binding is going to be whatever I collapse. So this is so abstract open books give me three manifolds together with an open book decomposition. The only problem is that this three manifold is only given for me up to diffeomorphism, because because it was a construction. Okay. I wanted to talk a little bit more about how to describe monodromies. So we need to understand what kind of maps I can have, and I'm going to call this the mapping class group of my surface. So these are the maps I can have up to isotopy. Isotopy doesn't change the diffeomorphism type of the octane manifold, so I really only care about isotopy, up to isotopy. And here's the claim of Dehn, is that these guys, so this is a group with composition, and this group is generated by the Dehn twists. Dehn twists are exactly the picture I already described you, is the map which takes this curve A into this twisted curve, tau alpha of A. Okay, so the way I'm going to do it is that I'm going to take the neighborhood of this curve here, and I'm going to apply this monodromy, this twisting on that annulus, and get back to the original picture. Okay, so in fact, Licorice also tells you that you don't need to consider all the Dehn twists if you don't want to. It's enough to consider a Dehn twist along these simple curves which I've drawn here. So it looks like sort of a basis for the manifold. And then, yeah, as just as I said it, this makes it very combinatorial to work with mapping class groups. So I wanted to give you one example of how you construct a three manifold from an abstract open book. So imagine that the abstract open book I'm having has page, which is an annulus, and the monodromy is the Dehn twist to the nth power. Okay, so let me just do this construction. So first I take the mapping torus, which is taking a annulus cross interval. I can even draw, so that's a solid torus, and it's going to glue this curve here onto when I turn around n times. Okay, and now I'm going to collapse every single circle here on the boundary and in the inner boundary as well into one circle on each. So there's going to be one circle here and one circle there. So this is the collapsed ones here and here. And now I have a solid torus, and I also know that this arc is glued to this arc, which I drew here. So this is the first part of the arc. So this is this one, and then the other one is on the back. It goes like that. So this one is an N1 curve, and if you remember length spaces, you know that this just gives you a length space Ln1. Okay. Yeah. So, and there's of course many other examples. Now I wanted to talk about how open books define contact structures, if you don't have any questions up to now. Okay. So here's the definition of what does it mean for a contact structure to be supported by an open book decomposition. So you have an open book decomposition. So remember, an open book decomposition was a binding, which is an embedded one manifold together with a fibration, and it is supporting a contact structure if the binding is a transverse knot. Remember, transverse knot was this; it was just transverse to the contact structures, and the alpha was the one form of which the contact structure was the kernel of, restricted to the pages. So the alpha restricted to the pages gives you a positive area form on each page. So this is not very friendly to work with. The way you should think of it, and this is how I'm trying to think of it, is that somehow the contact structure is near the tangent space of the page. So it starts horizontal because it has to, but then it will fairly quickly turn to be almost vertical, almost tangent to the page. Of course, it cannot be tangent to the page because then it wouldn't be a contact structure, because contact structures are not tangents to surfaces. But it's almost tangent to it, just like vibrates a bit around it, and it doesn't turn. It's very important. Okay, so Thurston and Winkelnkemper gave a construction showing that any open book supports a contact structure. So there is a contact structure for a given open book that gives you the for which B is going to be transverse, and the pages, the alpha restricted to the pages is going to be.
Sorry, so
Yeah.
basically, I mean, the alpha is a symplectic form on the pages.
Yes.
Thank you.
Yeah, except that the symplectic and area form is the same thing in 2 dimensions. But yes.
Yeah. Mhm.
Yes. Oh yes, but yes, because I could say the same things in higher dimensions. And then it would be more useful. Yeah, and here I might just skip this because it's only going to till 4 o'clock, no? So I gave you like an explicit calculation of why the contact structure, one of the contact structures, is supported by the open book I gave you. I told you. I'm going to send you the files and you can check it. Okay. And I wanted to give you a taste of how you can take an open book and construct a contact structure which it is supported by. All right. So you have an abstract open book. So this is a. I'm going back and forth between abstract and non-abstract open books, whatever is more convenient for me. It's usually just phrasing. So you have an abstract open book as phi, and you are and you construct this 3-manifold for me. This is the construction I gave you. So this part is the mapping torus, and this extra part here is collapsing the binding. And we can make sure that the neighborhood of the surface is preserved by the monodromy. And then I'm just cutting my 3-manifold into 2 pieces. One of the pieces is going to be away from the binding. So this is the part which is somehow away from the binding, and this is the neighborhood of the binding here. So the neighborhood of the binding is a solid torus, D2 cross S1, and away from the binding is basically a mapping torus. So and now I have to construct a contact structure on the mapping torus, and then I have to construct and extend it near the binding. So the construction on the mapping torus goes the following way. You just take an area form on the page, which has a standard form near the binding. Okay, it looks like 1 plus S d theta, and you show that these area forms exist. The set of such area forms is convex. And then you are going to take the one form. Sorry. What I wanted to say that d lambda is an area form, not the whole lambda. So if you have heard these things, this is like a Liouville form on the page. If that makes anyone happy. So you take this one form, and then you take t times the one form plus 1 minus t times phi star of that one form. So basically what I'm doing is that, I need to connect the one form with phi star of the bound form, and this is the way I can glue it together to have a one form on the mapping torus. And this is what I'm doing. So this lambda t is going to give me a one form on the mapping torus. And then there's a fairly simple computation just coming from this fact that this is an area form. which says that this lambda t plus k times dt, so where k is big enough, is giving you a contact form on the mapping torus. And now, once I'm done with this, I have this very nice local shape of lambda t near the binding, so I can just use it to extend it to the solid torus, which is inside. And this is what's written down here. So now I have to, this is how the one form has to looks like near the, so on the mapping torus, this is how the one form looks like on the mapping torus. And I'm going to look like for the one form in this form, in this shape. So FR d theta plus GR dt. And I also know how it should look like near the binding, because the binding is a transverse knot. And if you remember, we had a local model for how contact structures look like near transverse knots. And that was, I'm just showing it to you. That was fairly early in the talk. Here. So it had to look like dz plus half r squared d theta. And now I'm going back. Okay, so this is what's written here. I think I left out the half, which is not important. And now I changed my coordinates. So this 1 plus s is translating into 2 minus r if you use the coordinates of the solid torus. And now, and I also need that this fr d theta plus gr plus gr dt is a contact form. So now I'm drawing a picture. So how does it have to look like? Well, at the beginning, it has to look like 1 r squared. And at the end, it has to look like 2 minus rk. K is some big number. And the contactness, if you just check what is this alpha wedge d alpha being positive means, it just means that the FRGR and the derivative and the vector have to give you a positive basis of your of R2. So this vector together with the tangent vector has to give you a positive basis. So it has to somehow turn this way. That is the condition of being a standard, being a contact means. And now I can just connect it, and here is the connection. I just have to always go this way so that to make sure that it's a positive basis. If you do that, you will end up having a contact structure which is supported by your open book. And then what you then want to show that, so this one is already pretty good. And you can also show that this contact structure is unique up to isotopy. You can basically check it that near B it is unique because of the neighborhood theorem, and because of the convexity S of S, any two of them just can be moved to each other within contact structure which are always supported. And then I think I just ran out of time, so I can stop. But I'm happy to answer questions.
Thank you very much, Vera, for your talk. Are there any more questions or comments?
Maybe a quick question. How would this, I don't know if it's possible or not, I'm not very familiar with this topic, but does there exist a notion of open book, sort of like this bridge with non-coorientable contact structures?
I think there are, so is it true? I think it's true that non-coorientable contact structures are can be double covered with a coorientable contact structure.
Yeah.
And then I think you can say something there on the double cover. And so I was thinking about that and I got confused. That's the truth, but maybe it just works. Yeah. So non-correlative contact structure has not really been the focus of research. So it's not known because it's hard. I think it's not known because people just haven't really done it.
Okay. Thanks.
So any more questions or comments? Okay, so
Sorry, could you tell something more about the application of open book decompositions in a geometric dynamics, or just in dynamics?
I don't know too much about that actually.
Okay.
There's a recent progress in that about pseudo-analysis of maps, and I'm just reading up on it. So there's some very nice recent progress of, so one can understand. So there, it has always been a result that if you have a foliation, then you can make it into both a positive and a negative contact structure. That's been a result of Eliashberg. And recently it has been turned backwards. So if you have a positive and negative contact structure, which are in close enough to each other in a suitable sense, then you can turn that into a foliation, and you can prove theorems about foliations using contact structures, because foliations are non-rigid and contact structure are somehow rigid. Rigid in the sense that they are like somehow locally, they're not interesting. And I think something within these lines, you can also do something with pseudo-NSO maps, which I'm just learning. So I can't yet say too much about it. But there is recent applications which look very promising.
Okay, thank you.
So any more questions? No? Okay, so thank you again, Vera, for this nice talk. And thank you all for attending. Next week, we have Enrique Burschin from IMPA in Brazil, who will talk about Lie groupoids and Poisson geometry. So see you all next week.